Hey guys, welcome to Safi Next. In this video, I will derive two very important relations of the form given through these two equations. These relations represent two very important quantities respectively known as variance and standard deviation. From mathematical point of view, they are not very different quantities. However, from physics point of view, they are quite different, and only the standard deviation correctly represent a physical scenario. In this video, you will catch up the concept behind this point as well. Nevertheless, both these quantities are used for analyzing data obtained through repeatedly performing an experiment for measuring a physical quantity. They tell how much the measured value of the physical quantity deviates from the average of the data measured for the physical quantity. Additionally, these quantities are equally important in theoretical as well as experimental physics and are frequently used in statistical and quantum mechanics. To grasp this idea, let us begin from an example of discrete data. Let me repeatedly perform an experiment for measuring the value of a physical quantity denoted by x. Let me obtain value x1 and 1 times, value x2 and 2 times, up to value xn n times. Then we know from our videos on probability theory that the average or mean of this data is given by x bar equals x1 times n1 plus x2 times n2 plus up to xn times nn, the whole divided by n1 plus n2 plus up to n sub n. We can split this equation into this one form. In this form, the coefficient of x1, x2 and xn define the probabilities of their outcomes and can be written in the form p sub I equals capital Ni divided by summation over I n sub I. We see from equation 3 that the probability Pi satisfies the normalization condition, that is, sum over I p sub I equals sum over I n sub I divided by sum over I n sub I, which in fact is equal to 1. Substituting equation 3, equation 1 can be expressed in this one form: x bar equals p1 times x1 plus p2 times x2 plus pn times xn, and can be abstractly written as sum over I xi times pi. From the perspective of theoretical approaches to the solution of a problem, the probability pi in equation 4 is called a priori probability. To have an estimate of how much the individual values x1, x2 and xn of the data deviate from the average value of equation 4, we define the variance of the data. To this end, we first find the square of the difference of each data point from the average in the following way: delta x1 squared equals x1 minus x bar whole square, delta x2 squared equals x2 minus x bar whole square, and similarly for the nth measurement delta xn. Since each of these quantities is squared, therefore each of them gives a positive real number. Finally, we find the weighted average of the quantities in equation 5 according to the probability distribution pi, that is, we find the weighted average of the difference through this one equation where each difference is multiplied with its corresponding probability. And obviously this equation can be written in a very abstract form through this one summation, or substituting the value of delta xi, we can put it finally into this form. Since every pi is greater or equal to 0 and xi minus x bar whole square is greater or equal to 0, therefore delta x bar whole square is also greater or equal to 0. It is equal to 0 only if every xi equals x bar. Otherwise, it is greater than 0. The quantity in equation 6 is called variance of the data, or the dispersion of the data, and is usually denoted by sigma square equal to delta x bar whole square. From mathematical point of view, equation 6 is okay. However, from physics point of view, it is a little problematic. Since the variance is equal to the average of the square of the difference of a physical quantity, therefore its unit is square of the unit of that physical quantity. To avoid this difficulty, another quantity called standard deviation is defined through the square root of the variance. That is, the standard deviation of x is given by SD of x equals square root of the variance squared, which is in fact equal to the square root of this whole summation. Equation 7 defines the standard deviation, which is measured in the unit of the physical quantity x.